All right, everyone. So we're going to look through a past paper question today mainly. But I think I might just uh, scan through um, the PowerPoint here on radioactivity, right? To just bring back a little bit of stuff to our memory prior to us starting the lesson or the revision session mainly, right? Whenever you talk about radioactivity, one of the first thing that has to come to mind is um, half-life. And I mean, most of us would have learned some stuff about radioactivity in the past, right? I mean, radioactivity, of course, by definition, I think you should know a definition for radioactivity. Anybody know what radioactivity is?
Sir, can you please repeat?
The question is, what is radioactivity?
Oh, this would be the spontaneous emission of radiation in the form of particles or high energy photons resulting in a nuclear reaction. They usually give off the three ionizing radiation, which is alpha, gamma, and beta.
So, like, you're studying, man. You're studying?
Sir, I'm trying.
Isabel, would you agree with what she said?
Yes, sir.
Yeah.
It's
One
a
of the
spontaneous and random process.
exactly. Yeah, man.
Like,
So
if I were to add anything, I just add those two words because I know they give marks for them.
yes, indeed, those two words are paramount importance. That would be that it's a spontaneous process, right? And of course, it's a very random process. Nothing controls the process. It decays whenever it wants to decay, all of that kind of stuff. But the beautiful thing is that despite the the spontaneousness and the randomness about it, every element that goes through a process of radioactive decay has a set half-life for the most part. So even though the process is random, you can still figure out where and when the half-life will occur, right? So that doesn't change, so to speak, for the most part, right? Definitely. And one of the reasons why elements goes through decay is due to the fact that the element possibly is unstable. So whenever the elements are unstable, it's going to disintegrate into the alpha, well, giving off alpha, beta, or gamma. By now, you should know that for alpha, um, alpha is technically a helium element, right? Technically a helium element. When it comes on to
Yes, sir.
beta,
It has a helium nucleus.
hmm when it comes on to beta, we're dealing with an electron, right? And what I must say that this is a positive, this helium, what we're talking about here, it's not completely helium. I think I think it's a helium nucleus. I don't fully remember, but we know that it is positively charged. That's one of the main things we must understand. That this is it's a positively charged helium atom, I guess, if you want to call it so. I don't know if it's an atom, but it is positively charged. The beta particle is negatively charged. Um, what else? Then we know that in some radioactive processes, it can give off gamma. Gamma now is technically an electromagnetic magnetic radiation, which is technically light. All right, basically light that doesn't have any charge. Okay. Now I think in the process of studying about radioactivity, you should understand how these particles are deflected within a electric field and also within a magnetic field. I can't tell you how if they will ask you a question related to that, but in your studies, ensure you go through that. In addition to that, the thickness in terms of how they pass through materials, right? You must understand what how far they can travel in air. What is it that can block them? In this case, alpha, which is the heavier substance, will be stopped by a piece of paper once it is within close proximity to the paper, right? It doesn't travel more than, well, let me just say this. A 2 millimeter thickness paper, right, will stop uh, the alpha nuclei. They are the helium nuclei, rather, the helium nuclei. So those information you're supposed to know them. For beta, aluminum will stop that, right? And for gamma, lead is what we use to stop it. Okay. Now, in the process of radioactive decay and all of that, there are equations related to it. Okay. And this right here is just the root equation for the whole radioactive decay. You know, there is a proof that can be done, right? Not sure if they'll ask you to prove yet, but at the end of the day, you can prove back that what we just showed you a while ago to get this equation right here. This is the general radioactive decay equation. It is similar to that of the discharging capacitor equation. Whenever the capacitor is discharging, it looks the same way in terms of the structure. And if you were to plot a graph, this is how it would look. It's a discharging or a decaying type of graph. N in this case is the number of nuclei that would be remaining. So as you can imagine, if you're decaying a substance, right, and time is being passed, at the end of that time period, then you're expecting to have less substance because you're decaying the substances. I naught here is the initial amount that you would have started out with. E is the exponent, right? And you know this lambda symbol here is talking about what we call the decay constant, right? That's the decay constant. Then of course T is just the time period. Okay. Just scanning through all of this stuff here. You can go ahead. You really I would say you could try to see if you can prove this. Going into the exam, I don't know what they might ask you, right? I think the lesson is up and running on the site, so you can definitely go back to this and watch that part. There's another thing, what we call activity, right? Activity in this case is it's the same type of radioactive decay process. It's just that we just kind of collectively talk about it in a sense. So if you hear we talk about the activity of a substance, we're still talking about the decaying of that substance, right? If you want to find the activity of a particular substance, then all you simply need is the decay constant and the number of nuclei that is present within that substance. Okay. In just the same way, we can, talk about the decaying of a regular sample. In talking about activity, you can also have that decay process taking place. So this would be the equation, right? That says A is equal to A naught E to the lambda T. When you if you were to supposed to plot that graph, you would get a decay graph like this. So quite often they can ask you about this as well. So anything to do with activity, then to take into account this graph, to take into account this equation. The units for this decay process here is what we call becquerels. Alright. So if you were to use the equation up here, so that says A, so imagine that you have the time constant, the decay constant rather, and you have the number of sample, then your answer has to be in BQ, which is becquerels. Okay. I think those are the general stuff. Well, let's talk a little bit about the half-life. Half-life, as you can imagine, is that time taken for the number of the nuclei to decay to or reduce to half of its initial amount. So if you start off with 1,000, right? When it reaches 500, the time at that point would be your half-life, and that just simply means the time it takes for the initial substance to reduce to half. Now, what you must understand is that a substance can have several half-lives, right? So going to 500 would be the first half-life, right? So coming from 1,000 to 500 would be the first half-life. Now, when this 500 has been disintegrated to half of that amount, that will be classified as a second half-life. Now, the thing about it though is that the half-life is constant, meaning that the half-life from 500, from 1,000 to 500 will be the same half-life, right? That will be recorded here from 500 to 250. It will still be the same half-life. Okay, so it says that half-life is constant. So quite often, if you get a discharging graph like this, and they say find out the maximum number of half-life, then you can, you know, identify where half is, the next half, until there's no more halves remaining, until everything is completely disintegrated, and so on. Follow me?
Yes, sir. But wait, times and can you go back to it? Yeah. Oh, never mind.
All right. Okay. So I think we can run from here. So, but there's an equation though related to the half-life, and we can definitely derive this from all of what you're seeing here. But at the get-go, not sure if you will be asking us to derive anything. But one other thing you must remember now, that half-life is equal to ln2 divided by the decay constant. Okay, so this is one formula that must resonate in your mind. All right, let's see what this. Well, before we do that, I want to just remember something about the I think it's tectesium, right? Tectesium. Tectesium. Okay. We should look. If,
Yeah.
so you see when you're studying as well, let's go through your syllabus formula, right? So the topics on the syllabus that you know you're getting mainly, go through it, because they could ask you about this type of substance, right? I think this is pronounced tectesium, I think. So it's a very widely used radioactive substance in for the whole process of diagnosis, right? One of the main reason why we they use this type of radioactive substance is because of the short half life, and the fact that it also gives off relatively low gamma rays. Okay, so this is almost like a safer type of a radioactive substance to use in the body, because it doesn't it has a very short half life of 6 hours, and that give off a lot of powerful radiation, right? So it it's very useful. I think the first question that we're going to look at here is asking us about that same thing. So let's just see if we can proceed with this paper now. So it says that technetium, if that's what it's pronounced, is commonly used radioactive isotope in nuclear medicine. It says complete the table to indicate two properties and two reasons why a radioactive substance such as technetium can be used in this way. So one of the property here is that it has a half-life of 6 hours, right? Then now another property here is the fact that it emits low gamma radiation, I believe. right? So, and then now for the reasons for that, so I mean, having a very short half life will, you know, will get rid of the radioactive substance out of the body very quickly, which will reduce the chances of damages to the body and all of that, right? Or even causing harm to the body, uh, right? Then now similar thing to the fact that it emits low gamma radiation, so less damages to the cell, right? So less damages to to useful cells or healthy cells, right? So if you have less or low energy or low gamma radiation, then it's not going to damage much of the good cells in the body. And we said for this now, you know, the substance or the it will disintegrate much faster, right, within the body. All right. So that will cover that mainly, you know. But if you have any questions related to that, you can let me know quickly.
No, sir.
All right. So please just go back over.
But like,
Go ahead.
I was saying, these two properties wouldn't like the reason for them might be relatively the same.
Possibly,
It's less damage.
Yeah, yeah, technically. Let
Yeah.
me go back and see if I have any other information related to this. I think the information was somewhat limited at the time when I looked at this, but right, I think I guess maybe one of the next thing we could look at is what these are the two main properties though that I can think of. Right, these are the main two
Okay.
properties. Yeah, yeah, man. So
I guess it also disintegrates, like also something useful about it disintegrating quickly would be for, like, to I guess you could say, fix the tumors and stuff in time, because you don't want something that's disintegrating over 10 years. The tumors would grow too quickly.
yeah, so
Wait, can you please repeat that?
What I was thinking could also be a reason was, like, you'd want the um test netium to disintegrate quickly in the body, because you wouldn't want it to take too long to um destroy the tumors and stuff,
the thing
because
about
otherwise it would grow, the tumors and stuff would grow too fast, so
the thing
it
about
would be effective if it didn't, like, disintegrate quickly.
yeah, the thing about radioactive isotopes is that, or any radioactive substance, they can cause significant harm to the body, right? So using one that has a very short half life will get the job done in quick time and create less damages. That less damage now is also linked to the fact that it also gives off low energy gamma radiation. See what I mean?
Yes, sir.
Yeah. So yeah, that's no. Now you have a question now. It says that um it says a sample, right, of technetium 999 M has an initial activity A naught of 50 gigabecquerels. It says here its activity is measured at 2 hours interval and results recorded as shown in the table. It says complete the table by calculating and inserting the appropriate values. Okay, so somebody go ahead and help me out with this now. So what is the first thing we're going to want to complete in the table here?
Hello?
Yeah, you're not hearing me.
Sorry? Sorry, sir. Had some audio problems. Can you please repeat, please?
Yes, what I'm saying here is what is the first thing we're going to do here based on this question? What are we expecting to do?
Divide the values of 829.7. Well, first you have to change the gigabecquerels into units.
No, you don't have to change it. You don't need to change it. The reason why I wouldn't want to change it because you're essentially dividing um you know activity by activity. So the giga would eventually cancel out. You follow me?
Yes, sir.
So go ahead and give me the values, guys. I must let you guys know that going into the exam, you have to do something. You have to work fast, right? So all of what we are there, so it value 2 marks. So we shouldn't take more than 2 minutes to do it. If we practice to take forever to work a question,
Yeah, it's 0.79, 0.63, 0.50, 0.40, 0.32, and 0.25.
you made it 0.3 what?
0.79,
No man, give me
0.63,
0.3. 0.3 what?
0.32,
The next number.
0.25.
Mhm. That's it, no?
Yes, sir.
I think this is what we have here. If I missed out anything, let me know. So the next thing for us to do is to um, ln these values, right? So that ln button on your calculator, you will hit that button, then you put in the value 0.79. I get, let me know if you get a negative number now,
Yeah, 0.24.
right? Then now ln of 0. I only hope but these just look fictitious though.
Negative
Like them just look
0.69.
fictitious. Like I don't like how them look. They look fictitious. You know.
Uh,
I mean,
Sir, what year was this question?
eh?
What year was this question?
Well, I would have to go back and check. Honestly, I don't remember.
It looks similar to 2017, but I'm not sure.
Because these negative values now, I wonder what they're going to tell me to do with these negative values, guys. I mean, I think we're on the right track. That much I can say because all we're just doing here is to just simply ln the numbers, right? Mm. Yeah, I mean, yeah. So I guess no, they might just want us to plot a graph, right? So basically, you're saying it says on the graph you're provided, it says plot a graph of um, ln a slash a naught against time in hours. So we don't have to convert the hours. It is as is, right? We don't need to convert it. All right. So I'm pretty sure you guys have graph papers as well. It'd be good if you guys could practice this right away. But I would love to see what this graph is going to look like, honestly. I want to see how this graph is going to look. So, so these, oh, forgot that I didn't write down these values. You guys still with me?
Yes, sir.
I'm wondering though, like, is it a case that we always get this type of numbers? I don't know. But if you see something weird, I mean, just work with it. I mean, keep is weird. So, all right. So we know that time is gonna be down here. So the time I'm gonna do down there. So then now we basically having ln a over an a naught over here. So I think what I have to do is to get the negative numbers, right? I'm going to put time right here. I'm going to start the graph right here, right? So the numbers are very small, so I could say negative 0.2, negative 0.4, negative 0.6, negative 0.8, negative 1.0, negative 1.2, negative 1.4. Alright, and then now for the time now, could say 2, 4, 6, 8, 10, 12. Obviously we need to have a scale. I mean, scale is so 2 centimeters. So this is for the y-axis. 2 centimeter to uh, technically could say 0.2 units. And now for the x-axis, right, we say 2 centimeter to 2 units. So the first point we're looking to plot is 2 and negative 2.4. My negative 2.4 will be somewhere here. So whenever you're plotting points, put a dot, put a circle around it. Right? Then we continue 4. So we're looking for 4 and negative 4.6. Maybe this is not so correct. The first part might not be so correct. Let me check that again. This is gonna be negative 0.3. So that means to say 2, 4. Clear the boy, so. Alright. Sometimes this thing is so hard to read on the computer, so okay. I think I'm making progress. This is 1.1, negative 1.13, possibly somewhere so. Right, and then now the last one. So 12 gonna be just before we reach here, so about 3 point, negative 1.38 would be right here. So the next thing for us to do is to just plot a graph, or to just draw a line of base fit. Right? This could work as a line of base fit, ladies and gentlemen. It could work. I think that's what
Sir,
we
question.
Yeah.
Did they ask to include the draw best fit line, or do we have to just like include that no matter what?
They will tell you from time to time. Let's go back to the thing and see what they instructed us to do. Right? So it says here to draw best, best straight line through the points. Follow me?
Okay, sir.
Yeah.
So, all right.
It's a 4 mark question that I can say. You guys still trying to do it or what?
What was that, sir?
Are you guys trying the graph? Yes or no?
Yes, sir.
Yes, sir.
All right. I believe you would have the values already.
So could you just go over one thing though? Could you go over like measuring half-life like directly from a curve and a straight line?
Come again?
Like you know how you could measure like half-life directly from a curve and then you could also measure half-life directly from a straight line?
Yeah.
Could you just go over those two things like when we're done with this question?
Okay. So yes. Um. In the meantime, yeah. While you're working, I'll explain a little bit as it pertains to that. So you can determine the half life from the curve, right? But from the straight line, it is not so clear or straightforward to determine that, right? It is not so straightforward. But what we're going to do here for this particular graph question, we are going to find the decay constant using a straight line. By the way, I have less than a minute. I'll restart the session and then we'll pick up from here. All right. Okay, perfect. So as I was pointing out, right, that if we were to if we were asked to find the half life from a particular question, right, and it's a curve mainly, right, then we can essentially find the half life from the curve easily, but technically not, you know, from the straight line graph. So so in this case, imagine that we start out with a known sample, a known amount of a sample. Let's say 100 grams of the sample. Then you know that this graph is going to be n because n is talking about the sample. This part is going to be talking about the time. Now, we said half life is simply put the time taken for half the half of the sample to reduce to, let me say it again. So the half life is simply put the time taken for the known sample to reduce to half, right? So you start out with 100. What's the time it will take to reduce to 50? That time when it takes to reduce to 50 will be the half life. Cool? So from the graph, all you simply do is once you identify the the half of the initial amount, you just go across wherever the line touches, wherever this horizontal line touches the graph, then you would just read the corresponding time value. And that time value will tell you what the first half life is going to be. Okay? Any questions?
Yes, sir. No, sir. No.
Okay, great. So that is what we would do there. That is for when we're dealing with such type of a graph. No, we're not dealing with that at the moment. Now, they say that they want us to use the graph to determine the decay constant. Remember that the decay constant is lambda, right? This is what we're trying to find. Now, remember, just now I would have shown you an equation pertaining to activity that says A is equal to A naught, right? E raised to the time constant multiplied by the time. Now, the graph that we have is a ln A divided by A naught versus time graph. What we're going to do here is simply restructuring this equation so that we have ln A naught on one side and have t on one side. So what you would be expected to do
Sir,
here? Yes, go ahead.
I'm sorry to cut you, but could you go back at that, please?
What?
Um, at ln.
So remember now, Campbell. What are we plotting on the graph? Hmm?
I'm sorry, sir. What was that?
What are we plotting on the graph? Isn't this what we're plotting on the graph? So this is my y-axis.
Yes, sir.
This is my x-axis. And we have better graph looking like this, somewhat of that nature. Right? So we want to find the decay constant. But one of the things we must do, we must be able to can see my y variable and my x variable in this equation. Alright? Now, in order for me to can see that, what I'm going to do here, I'm going to transpose. Right? The first thing I'm going to do, I'm going to have a upon a naught. A upon a naught is equal to e times the decay constant times the time. Now, whenever I want to get rid of e, I have to times ln on both sides. Right? This is in a bracket here. So all I'm doing now is, multiplying both sides. Both sides by ln to cancel or to basically get rid of e. Because we know that ln and e is equal to 1 technically, right? But there's another thing that must come back to memory, and I'm going to show you. So when I do that, I have ln times a divided by a naught is equal to ln e times this thing in the power here. Once we have ln and e and the thing in the power, mathematics and the laws of logarithmetic or logs tells us that that thing in the power can come down in front. So if I have ln e raised to lambda t, technically I can have the time constant times t times ln e. So technically that what is in the power can come down. So it doesn't affect the operation. That is what the laws of log tells us. If there's something in the power and where ln is, right, like that, it brings it down in front. So once we now have that, we have ln a upon a naught, right, equal to, so we say that ln and e is equal to 1. So what we're left with now is the time constant times the time. So technically speaking, at this point, to use the graph to find the decay constant simply means that it's for us to find the gradient, because clearly this is my y variable, t is my x variable. Then whatsoever is remaining beside of it becomes my gradient value, since we're now linearizing this equation. Okay? This question makes sense because what? The line basically passes through 0. So there's no c value. So c is really equal to 0 based on how the graph looks. All right? So we can see that the equation or the line makes sense because it passes through 0 technically. So what we just simply need to do now is to go on the graph. We just need to go on the graph, pick 2 points. Whenever we're picking points on the graph, guys, right, we should pick points that are easily to be identified, so that you don't go through a lot of problems. So I could possibly pick a point here. When you pick that point, you need to pick another point which is approximately 75% away from each other, or takes up 75% of the line. So these are my 2 points that I'm going to pick. So let me see if I can read off the values. So we know I need a x1 and a y1 value. So this one I'm going to call this my x, x1, so that's going to be 1. Then now for my y value, that's going to be negative 0.1, we put the 0.12 technically. Then now we know we need a x2, we need a y2. Because I can't really see this correctly or properly on the graph, but you can. I know that this point is going to be 10. Then now the other value is going to be negative 1.1, you know, 1.1, let's say 1.12 for argument's sake. So all we now need to
Sir,
do,
you can't use, well, for this part, you can't just use the accurate values from in the table.
no, no, you shouldn't. You shouldn't, because whenever you draw the line, there are times when those values, they don't pass through the line. Because when you look on the value here, what if you make mistake and use this value? This value in the line, you know. So it would throw off your values. Technically, whenever you're finding gradient, it has to come from the line. However, it should not be the points that you plotted on the line initially. Because not all of my points here pass through the line. As you can see, they are genuinely you know, uh, only a scratch of them really pass through. They're about. So what I mean?
Yes, sir.
In addition to you finding the gradient, you should identify those points. So just like what I did, I use an X to identify those points. So rule of thumb, if you want to use X when you're plotting the points on the graph, you can use X. But if you're finding the gradient now, you use dot to simply signify that is talking about the gradient and all of that. There's also another way how we do it as well, is to draw a triangle thing here, right? This now kind of guide you a little bit better. You would use your ruler to do such a thing, right? Then from that now, you have garner, you have pick up your values. Then from there, so we go and calculate the gradient. Gradient, we know, is equal to y2 minus y1 divided by x2 minus x1. So I would have broken it down already to just identify these points really. So my y2 is minus 1.12 minus, put a bracket here, my y1 is going to be minus 0.12. Divide that now. x2 is 10, right? Then the next value here is 1. So we'll go ahead and do the mathematics here. Technically, these values in between here, the minus and the minus are going to become plus technically. So what we would have is that minus 1.12 plus 0.12, right? That is what the numerator would have, and then the denominator is going to be 9. So we say minus 1.12 plus 0.12, you get negative 1 in the numerator, right? So negative 1 in the numerator and 9. So gradient is technically equal to minus, would it be? No, I'm lying. That's a lie. Let me just fix that. You can leave it as negative 1 upon 9, you know. I don't like the whole negative values really, because it kind of want to kind of show me off to some degree, but I think that would be the answer though. So let's see what I'm asking now. Let me just confirm something here because I'm pretty sure in that equation it doesn't have any minus sign. Yeah, it doesn't have a minus sign. Right? So in essence, I, I, I would say the decay constant is equal to minus 1 upon 9. I really don't know if there's something incorrect about this thing, but that is what I would go with at this point in time. I've never really seen the decay constant being a negative number before, but that is just what I got here. Not sure what is happening, but I think that's that. It's a little bit tricky though. Um, because I really don't want a negative number, you know. But let me know if you guys have any concerns though. Any questions for me? I wonder if you guys gone. Are you still there?
No, sir, I understand.
Oh, no. Guess what? No. I think the equation, there's something that was left out of the equation. Um, so right here, there's supposed to be a minus sign. I was thinking, but I never know that I left it out in the PowerPoint. So there's a minus sign here, so let's go back. So remember, there's an equation that says n is equal to n naught e to the minus, right? And then we have another one that says a is equal to a naught e to the minus this, that. So they are the same thing. So please forgive me that I left out this minus sign because technically no, this is minus right here, right? So hence how you get a positive value now for your decay constant. So really and truly, a decay constant is 0.11, and trying to ascertain the units for this. The units for this, I believe, is seconds. You know, I believe the units for this is seconds, based on what I see here in the book. So please just make sure so you have the equation correct. All right. Okay. No. Yes. What are they trying to find here? Sometimes these books just leave out some information. Something I really wonder, like that that's not the unit. The unit is decay constant per second. So it's per second. Per second. So that's the unit. So I think we are right.
Wait, sir. The unit is per second for the K constant.
Per second, yeah. So the next part of the question here now comes to us to say that it says use the decay constant to calculate the half-life. So this is where now that thing comes into play, that we say that the half-life is equal to ln 2 upon the decay constant. So that lovely formula that we know of. So ln 2, if you put that in your calculator, you're supposed to get 0.693. Divide that by the decay constant, which is 0.11. Right? We get a half-life of 6.3 hours. Okay? That would be our half-life. We all right?
Okay, sir. Yeah, is the half life always in hours?
No, it's not always in
How do
hours.
I know when it's
It
like
can,
in
it can
seconds
be
or
in
something?
years. So based on the question that was given, the thing was given in hours, right? It was given in hours. So give me a second here. Hello. No, I'm in our class, brother. Can't do that right now. Might as well. Yeah. So based on this theory here, because remember now technetium, we said that technetium has a half-life of 6 hours already, right? Give me a second, guys. Hello. Yeah, man, we out there, man. We live, who? 61. Burger fries and chicken. All right. All right. Okay. So because we remember technetium has a half-life of 6 hours, so we have to be sure that we're specifying that the answer is in hours, basically. You know what I mean? So that would cover that really. So
Okay.
based on this, we see we never really make much of a blunder in our calculation, so to speak. So we are on the right path. Because on the mere fact we get about 6.3 hours, then we know, say, all right, something is right. Wow, I never realized that I never finished putting together the PowerPoint.